It's CPU architecture time. But not yet. First, I would like to go back to the 3-bit decoder, because in the previous two videos I asked for feedback on how to improve basically a bit decoder multiple times. And there was some discussion, and I got multiple, well, when I say multiple, I basically mean 2 or even 1, depending on how you want to count it. Different solutions for how it can be implemented. And both of them pretty much work, or what do you build on? They build on this system right here. I did explain this when I was replacing the knots with these decoders in one of the previous videos, but just to remind you real quick, basically this 1-bit decoder on the most significant bit decides whether we're in the first half or the second half of the output. Then the second one, once we know which half we're in, the second one decides the half of the half, and so on and so forth, and this can be scaled to an arbitrary number of bits or layers. Now, instead of using these ends, it is actually possible to apply a bunch of decoders like this, chain them together, have switches on their outputs, and that way we can have a n-bit decoder built out of basically 1-bit decoders. So I'm gonna try to build it right now. I don't think I'm gonna actually put that on video. I'll just build it offline, off camera, and I'll be back once it's done, and we can discuss it real quick, because that's not the point of the video, I realize. So BRB. There we go. Now, I can already hear you scream, how on earth is this better? Because this looks, to me at least, this looks much more complicated than the original grid solution, right? This seems pretty simple, a bunch of ands and that's all. Well, this is a complicated multi-step contraption that does some complicated thing. Well, there's two things here really. I'm still not sure how expensive in terms of NAND core and AND gonna be, but long story short, it seems like this might be cheaper if you consider a switch to cost the same as an AND. But even so, the more important part of this here is, yeah, I will, by the way, Kirby. Yeah, I will remove this on. We'll get to that later. This is just for clarity. So let's see what this does. First of all, we have our green line. You can see it's always on. And what the green line does is this is gonna be piped into the output. Actual inputs never interact with the output. Actual inputs are only ever piped into decisions. Right? They're piped into decisions, and then decisions are piped into enabling or disabling switches. And kind of intuitively, this signal never intermingles directly with this one. So that's one thing. Now, what do the different lines do? Well, just like with the previous solution, this guy, the most significant bit, goes into one decoder, and basically it decides if we're going up or down. Let me remove all the dust signals. This decides if we go up or down. So at this point, as soon as this decoder is done, we already know that we're going to be piped up here or down here, right? Wait. This looks unconnected. I messed something up here. I messed something up. I need another connection. How can... Yeah, it doesn't work. Sorry. Let's fix this real quick. It's we're supposed to have another wire going down here, like so. yeah, I don't know how it got broken. I think I just tested it and it was fine. But yeah, you can see that once we pass this decoder and these two switches, these lines never actually intersect. So you can trace a boundary between them, right? And this boundary goes exactly in between these two things. So like so, you can see it, right? And the exact same thing actually happens at the second gate, at the second step. So now we have the second most significant bit. It goes into two decoders now, although it is sufficient to look at just one, and there's two simply because we have two exactly equivalent paths, right? We have up and down. That's why we need to have two decoders for up and for down. But basically this guy does exactly the same thing. It decides whether we're going up or down, and again, we do not intersect. So this is actually a perfectly balanced binary tree, is it not? Yeah, it is. And so, while in my opinion this is not as readable and as understandable as the AND, or, well, yeah, it probably isn't even as easy to understand, but this does precisely encode the idea of turning up and down on every bit. And this also scales. We can add another bit. We can add another row of these, like so, you know, and then rewire everything up. So that's one thing, right? This scales up, unfortunately, the thing I hate. But this scales up, right? We will have another line of decoders, and then we'll have another line of stuff. But it does scale. Now, you may notice an always on here. This I just put for readability, because we always need some signal to pass, right? We always need the signal to pass to some of these, to one of these outputs, no matter what happens. And that's kind of what's encoded here. And I did this for symmetry and for understandability, for readability. But this can be optimized quite a bit if we notice that this on and this decoder and these two switches are actually redundant, and we can remove the switches. And we can just use the decoder itself as an equivalent thing. So let's check. Yeah. So this can even be reduced like so. I don't think this kind of optimization scales. I think it's a one-off thing. But yeah, let me apply colors so that we're nice. Oh, whatever. So hopefully you get the idea of this. Now that we're done with this, I'm gonna proceed to the second suggestion I received, which is also in my books relevant to the 3-bit decoder, and it's a suggestion for the logic engine. Now remember how at one point I pondered whether I should use muxes or switches here? Right? And I basically just immediately threw out the muxes and decided in favor of switches, because the switches had gray pins, and I wanted to combine them. Well, turns out it is possible to do this with muxes just fine, and all we need to do is have two muxes like so. We have our 4 inputs. Let's see. I haven't actually thought this through entirely, so I'm kind of thinking as I go. But we have 2 muxes. These are our four inputs, or 4 outputs, 4 results. We pipe them like so. We decide which one we want using these pins. Then we pipe them, and among these 2, we decide which one we want. And that's the answer. And these, of course, come on. These will go into our bit thingy, into our bits. So I'm gonna implement this instead of the decoder plus switch contraption I have. I'm not actually sure. I don't remember what a mux is exactly. Let's see. Let's take a look at what a mux is. wherever that was. Must have been a while ago, I guess. Not searchable. Was it the multi... Okay, I'll be right back. Right, it's an input selector. Here we are. Yeah, so, and you may notice, actually, we could probably improve this. No, we cannot improve this yet because we don't, at this point in the game and in the campaign, we don't yet have a 1-bit decoder. But this is exactly the 1-bit decoder piped into 2 switches, right? So this guy gets decoded, gets piped into 2 switches. And that's exactly what we had over here, right? 1 decoder and 2 switches. This is the building block of our logic. So yeah, that's why I'm saying this is relevant to the 3-bit decoder, because over here we're actually finally going to be able to fully make use of these muxes to implement equivalently implement what is effectively a 2-bit decoder. So I'm gonna do that and I'll be right back. Actually, you know what? Do let me know in the comments if I should cut out more of what I do, you know, do more removals of wiring jobs, or if this is more interesting live. But I think I'll do this one live. So let's see. We have our 4 inputs. Let's not bother with them for now. And this is actually kind of an inverted pyramid, interestingly enough. Yeah, because instead of turning one on into 4 different options, we are rather converging 4 different options into one. So that's kind of an inverse of what we used to have, in a way, right? Except, so we would have our on here, and that would be our untouchable signal, right? That is just decided using logic. And here we have our untouchable signals coming in, and we are deciding using logic. But instead of being a single byte on, our untouchable signals are actual bytes. Did I say a single byte? A single bit. Right, by on. So yeah, this should be fairly simple, right? The second mux decides whether we are up or down, so this is the more significant thing. And these 2 muxes are exactly equivalent, and they are related to input 1. There they are, I don't know, decided by input 1. And now we just wire, except I need to be very careful what I wire. Where? Let's see. So I think I put them left to right, or NAND nor AND. So, and the first one is gonna be, yeah, it's the same order. So let's do an unclean job for now. This, and this. And this is gonna be our output. Let's see how this goes. It worked. Cool. So yeah, now we have used a bunch of muxes instead of the huge contraption, which I think might even save our score a bit. I'm not sure. But this does look cleaner, and I think this is easier to understand, much easier than the switch. So thanks for the suggestion. There's more stuff here. And by the way, shout out to Yotanido as always for suggesting the thing I'm gonna talk about next, and to Christopher Iman4921 for the mux suggestion. Muxes would actually be a good way of thinking about the problem in Logic Engine. Yes, exactly, they are. Thanks for the suggestion. Yeah, and these things I could actually derive using the 8-bit gates I already have, and that is OR and NOT. Because of course, OR and NOT is a complete system out of which I can build a full computer. I'm not sure if I'm gonna do that. I might, but I mean, considering the fact that we actually get the gates after completing this level, that seems a bit pointless. And besides, that's gonna be wasteful. That's actually gonna be very wasteful in terms of NAND score. But yeah, that's a good catch. I didn't even think of that I could derive these gates from OR and NOT. So thanks for the suggestion. Okay, I'll clean this up slightly, and then we'll finally proceed with actual levels. Like so. And let's proceed. Now, finally, the big reveal why I went back to the 3-bit encoder and all the stuff before proceeding. Let's go for arithmetic engine. Ta-da, we're back to our... Oh, we're back to the messy solution. What? Okay, but basically, turns out we keep our schematic, and we're asked to add more instructions, such as addition and subtraction. But I would like my nice solution, please. Maybe it's because I didn't run it. Onwards. Are you nice now? Cool. Right, so exact same thing, except we need to add more stuff. So adding of more stuff, I don't think is gonna be a problem at all. Right, we just add addition and subtraction, which is addition of negation. Oops. And I think, yeah, I finally get these gates. So I'm actually going to replace the huge ones with the small ones. Yeah, I expected I might need to save space by actually building the stuff out of OR and NOT here, but looks like I don't have to. So, yeah. All right, let's start by removing the huge ones, and I'll be back. All right, so we're gonna have an OR, a NAND, a NOR, and an AND down here, and we're also gonna be adding addition and subtraction. So add should be fairly simple. We won't have any carry. We'll just add 2 of our inputs, and we'll also disregard the carry out. Just pipe it into dev null. And for our subtraction, we will want to add a negated number. So that should be all, right? Except it's slightly unclear to me which number is supposed to be subtracted from which, especially considering these inputs are not input 1 and input 2. But I'm gonna assume red is input 2 and green is input 1. So let's connect that up. You know what? I'll also cut that out. Cable management is starting to get more and more difficult, because see, this is my output 1, this is my output 2, this is my output 3, this is my output 4. I'm kind of running out of space here. And yeah, here I even have a conflict. So can I do something like deselect that, please? Well, whatever. Oh no, oh no. Okay, let's remove these for now. I just want to move these guys over to the other side, but this is unsustainable. I don't think if I'm gonna be adding something like 256 instructions, this is gonna be a problem, right? So okay, just slightly higher than that. That's oops. No, I connected the wrong thing. Okay. Yeah, just as I said I wouldn't wire things on camera. Well, I felt I had an interesting thing to say about wiring. Right, this is getting, these buses are getting more and more complicated, larger and larger and larger. So yeah, this is my output bus, kind of. Not sure how I'm gonna pipe it. But now there is a new challenge in that I need a 3-bit decoder, basically. I think I just implement 3 bits, and that's enough. So I just add 4 muxes at the start, and that's all. And then I just pipe the 4 into. Well, actually, wait. Yeah, I will need 1 piped into them. Then I will need bit 2 piped into this. Okay, so I will have to do a complete rewiring job of this. Let's remove this stuff. Let's keep that, I guess. So I want 4 muxes. 1, 2, 3, 4. They will connect up per usual. Except it's so untidy. This is so untidy. You can't tell what's happening here at all. Oh well. I'll figure it out later. So now 1 just decides between these guys. This is my... Curiously, in this kind of situation, I make the decision, the least significant decision first, and then the most significant decision comes last. But yeah. Okay, so then I want 2 like so, and then I want 4 kind of like so. Sure. And then my my 8 inputs will not fit in here. So guess I'm moving everything somewhere else. Oh no. Oh no. Okay, I guess let's do something like this. Something like this. And then I'll have, this is my number 1, 2, 3, 4, 5. I only need 5. Okay, so I actually don't need this mux at all. It's unnecessary. And now I piped. Okay, I think this is clear enough. I'm gonna pipe this, and I'll be right back. No, it is not clear enough. Because you see, here I get a continuous ribbon of cables, just the way I like it, and it's fat enough to actually interfere with these guys. So when I'm trying to connect the first input or the first output, I interfere right here, and I actually don't know how to solve this. I probably need to come up with a better strategy for laying things out in general, because this is... I expect this to get very frustrating very quickly. But, well, for now this works though, so let's finish it up. Wait. Insufficient. What? 1, 2, 3, 4, 5. Oh, I have 6, even though the number is 5. Of course, the count is 6. That's okay. And I just barely fit under my input. What is this? Oh, this is the instruction. So yeah, that will need to get piped back up here. And these inputs, green is first, red is second, whatever. And I think that's it. Wrong. Input 17, input 178. code NAND. Wait, I get the short. Oh, okay. I just wired it. I just wired the inputs wrong. Green wired here, and red needs to be wired to red. That's fine. Now we're good. Wow. Okay, this is quite the debugger message. You know, when your schematic doesn't work, and all you get is wrong short circuit. It's broken. That's gonna be fun to debug, I imagine. Okay, so this is done, but I wonder what I can do about these issues right here. Because that's not gonna... How do I arrange these things? Do I have maybe something like directionality? So that all of my main, air quotes, buses are parallel to each other? And then I just communicate between them? Or what do I do? How do I do this? I mean, I think I can in principle rearrange this nicely, but I still don't get the general idea of how to wire things well. But yeah, I think I can do this by just rearranging my inputs or my actual operations like so. And then I'll have a single huge bus at the end, and it goes straight up, and that's what I will get. But how else do I do this? Really, the wiring becomes the challenge. It was not nearly as difficult to implement the thing as it is to wire the thing. Okay, I think for now I'm just gonna arrange them like so. I'll have inputs going here, I'll have outputs piped out here, and that'll be it. So 3, 2, 1. Right, I guess let's call this it. What's up? A custom component called ALU already exists. Do you want to overwrite it? Manual entry, component factory. I don't know. Keep both. Overwrite, discard. Keep both. Let's not delete anything, especially since I don't understand what's up with the custom component. Is this gonna be saved as a custom component for me to use, or what? Is this the ALU? Okay, let's check the manual entry. The component factory by clicking this button in the upper left bar. Don't have it yet. Okay. Component factory allows you to create your own components. The logic you place determines the behavior of the custom component, and the layout determines the shape. Alright. The input and output components you place become pins on the component. I see. Like with other... Okay, so these are Factorio blueprints. Basically, I assume I can build something once and then encase it in a small looking gate thingy element component. Which, by the way, looks like the canonical name for these things is component in this game. So you have a NAND component, an AND component. And is this my ALU component? Alright, the input becomes, so like with other components, the component output leading back to its input causes a circular dependency, outputs having a path back to inputs. What? Causes a circular dependency for custom components? What? Deja vu? It's the same thing I just read. Like with other components, component output leading path, outputs having a path back to inputs cause a circular dependency for custom components, even if the insides of the component would suggest there shouldn't be one. I see. I should finish reading sentences before getting confused. Not having to worry about the inside components reduces the complexity of larger builds. However, this strict abstraction can be inconvenient under certain circumstances. Yes, I can imagine that. In that case, use the unbuffered pins. What's an unbuffered pin? They allow bidirectional flow. And use the insides of the component to check for circular dependencies. Bidirectional flow. It's not entirely clear to me how a pin can have one directional flow, because as we know, if we put, right, we've used this a bunch of times, you can have a system like this, and this pin will both take a signal in and it will kind of let it out of itself. So it's a through pin. Though I guess what's actually meant here is that the pin allows the signal inside the OR, and also if there's a signal pipe to it from within the OR, it will spit it out. Okay. Probes placed in custom components which will show on their layout and can display values inside. Probes can be connected to other custom components so that deeply nested values can be displayed. I don't understand what probes are yet. I guess I will learn it in some point. Okay, values probed in this way can also be connected to the program component. What? For the component factory, the file manager also manages the custom components. The file names decide the component name, and the folder structure decides the component placement. Wait, do you mean the file manager as in the file manager on the OS on which the game is running? Or is there a built-in file manager? I see, component factory up here. Welcome to the component factory. The circuits you create in here will be usable as components in architectures. The circuitry you create defines the behavior of the component. The layout defines its shape. It's not entirely clear to me how the layout defines the shape, but okay. Components can be added, renamed, or deleted using the schematics menu. Since this level is a tool and not a challenge, you can go to the level map and continue on when you want. Oh, so... Ha! I see, I just clicked here, but the level called Component Factory, aka Abstract Singleton Proxy Factory Bean, is just a level. Okay. Wow. Custom, ALU, ALU1, ALU2. Huh. I don't understand what's up with the layout though. What happens if I click here? No, that's not my... Oh, I have two ALUs now. Wait a minute. Back. Cool. I saved two ALUs, and this is a better ALU. Okay, so there kind of is an incentive if you're building a component in a factory, there is an incentive to make it small, or at least make it neat in some way. And this answers my question about where inputs and outputs are. Although honestly, if I'm placing my own inputs and outputs, I would probably just make everything a square and force inputs outputs to be at the edges of the square, as opposed to this insanity. How does this interact with... Okay, no, but yes. You can fit stuff inside, but you cannot. And this is determined by, I'm guessing, both wires and... Also, I can fit a wire in here. Does this mean there's a place for wires in my ALU2 component? Like this here is the... Yep. Oh, and by the way, something I forgot to talk about is actually turns out this mux is also unnecessary. Even though it would be if we had more inputs, but this is just pointless. So that simplifies my schematic quite a bit. Both simplifies it and makes it more NAND efficient. Let's say this is the way. I have run it. Nothing has happened. Save it now. Back. Have I... Is it gonna be saved by default? I changed it. Is it saved now? Well, I will play around. Okay, so this looks saved. How do I delete the bad ALU? Manual, switch schematic. I see, ALU2. So this is my bad ALU and this is my good ALU. Okay, I might play around with this and make it smaller. But I think for now it's fine. We can proceed. Let's delete this guy. Wait, how do I delete this guy? Let's rename it to ALU bad. Whatever. ALU2 becomes ALU and ALU bad gets deleted. Yes. Default. What's default? You're no default. Okay, I think I get it. I'm not entirely sure what all these are. IO and yeah, these I'll know. I don't know what IO is. Probe. Yeah, probes and output and input. Yeah, so these, I'm guessing these probes are just debugging information. And these are just different kinds of inputs, outputs. But I think I'll actually play around with it when I feel the need to create custom components, which for now I don't exactly. Do I proceed with registers? Or do I call it a day? I mean, I have only done one level, basically. Let's take a look here. Time to create your master project, implementing the Overture computer architecture. This will be an actual Turing Complete machine, a true computer in every way. Woohoo! Turing Complete machine coming up. Oh, so I am now on track. Yes, there's a straight track leading me to a Turing Complete machine. An actually Turing Complete machine. Inside of the Turing Complete game, on my Turing Complete computer. I have logged the red components, well, sure. The mess you make from now on is saved between levels. I've already seen that. In this level, you need to create a circuit which can copy from a source to a destination. The instruction byte in this level determines the source and the destination. Okay, so 3 bits for destination and 3 bits for source. Kind of weird that destination comes first and then comes source, but that's fine. Source and destination can be one of 6 registers. Oh, I see. It can be one of 6 registers. These are reg 0, reg 1, reg 5. Sure. Additionally, this map has a dedicated input component. Wait, which can be the source and an output component, which can be... Oh, I think there's a comma missing here. This map has a dedicated input component, which can be the source, and an output component, which can be the destination. So we have input source and output destination. So yeah, basically this is to save and that is to load, I guess. Input unused, output unused. I wonder why is it unused? I mean, you might as well have put 6 registers if you have an unused signal. You know? Get a more intuitive understanding of the requirements. Click the instruction icon. Wow, there's a lot here. A lot new stuff happening. Oh no, I get this. I get this. No, I understood this. Output, yeah, no. Except, no, I haven't. These 2 bits are completely unused, are they? Bits 4, 5, 6. What about bits 7 and 8? Yeah, bits 7 and 8 are completely unused, so... Okay, I'm not sure I'm gonna be doing this right now. This looks like a bit of a challenge. How about we take a look at another space constraint level. This level has a value input and 3 condition bit inputs. The 3 bits select the conditions. The condition is shown below. Check the value against the selected condition in output. If it is satisfied... Oh, so we're implementing an if. Wow. 3 bits select the condition. That's a lot of conditions. 0? Well... I mean... These are negations of each other. So I only need 4. Well, I only need 4, you know, pieces of logic, and then I negate them, and we're fine. And even then, really, I only need 2. I need equals 0 or less than 0, or I need equals 0 and less than or equal to 0, and the other one I can derive. So yeah, it's basically I just build 2 things, and then I derive everything else from them. Okay. Okay. And this is a 3-bit decoder, which helpfully we have. Yeah, I think I'm gonna do this one. And next time I can start on the actual full track to the Turing Complete machine. Okay, let's keep the problem statement on screen. So never, yeah, don't care. This is just getting decoded immediately. Wait, what? Are you a byte? What are you? Are you a byte? It doesn't say. It only tells me, it only gives me 3 bits here. I don't have 3-bit things. Yeah, so that's, I'm guessing that's a byte. It's weird because previously we've had levels where we had byte inputs in which other, so right here even, right? We had this and everything else other than the 2 bits is unused. But still this had a byte interface and that thing has a 3-bit interface, which is weird. But okay, I guess. So yeah, this just gets decoded, no problem. This just gets decoded by a decoder. We already know how to do this. And yeah, that's all. And this is our value. Okay, so now all we need to do is we need to implement equals 0. And, well, we'll see what's easier. But I think less than 0 is probably going to be easier. How do I check for equals 0? Well, first of all, what is a 0? A 0 is all zeros and all zeros byte. I don't have anything mathematical. I mean, I could negate it and check if it's equal to itself, but it doesn't seem any more efficient than just comparing to 0. Also, what is comparison? That's actually an interesting question. And by comparison, I mean equality comparison. So I need all the bits to be the same, right? But I need the output to be a single bit. Which sounds like a huge matrix. Right, I have 2 bytes. I have 2 bytes. Well, I don't really have 2 bytes. I only need to check for 0, which I could just implement using... So if this is my input and I check equality for 0, I could use something like this, you know, and then is this gonna work? No, this is not enough ores, unfortunately. All right, yeah, I still have 2 here and 2 there, so I guess 2 more ores like so. This can check not equal to 0. That's better still. Wait, what? Yeah, like so. Well, it doesn't matter. I'm not making it neat for now. So this is kind of my not equal to 0 check. That's fine. That's fine. Let's now think about less than 0 or greater than 0 or something. Oh, okay. If we're talking about comparison now as an ordered comparison to 0, then we mean signed integers, right? Because if we had unsigned integers, then we would always have greater than or equal to 0. There would be nothing to reason about. But if we're talking about signed integers, then of course immediately we know that our negativeness is determined by 1 bit. It's the final bit. It's this guy. It's this guy. That's all. So, wait. Oh, I never talked about this in any of my official videos, have I? I actually, at one point, I went back and tried to make sense of 2's complement, and I ended up with a bunch of conspect like this. It is a video, but it is unlisted. I guess I'll put it up here, so check it out if you're interested. But let's take a look real quick. I don't have anything nice for... Well, let's just take a look at a single byte. So long as this thing is switched on, we are gonna be less than 0, aren't we? Because this is 127, everything else is 127, and the largest value we can have with this bit on is -1. So we're strictly greater than 0, which is good. So again, this on means greater than 0. Let's see. You know what? I'm even gonna do a comment on the wire. This means greater than 0. Exactly, this is exactly the Boolean value for greater than 0. Wait, sorry, less than 0. This is less than 0, and this is exactly the Boolean value for not equal to 0. Well, there's different notations, but I'll use this one. Oops. What's up? Okay, the wire's too short. Okay, now that I have these, I am pretty sure I already have the solution for everything else I need. I just derive it using logical connections. So now it's just time for me to consider how to lay things out. And yeah. Well, you know what? I'm gonna start with just making this tidier. I think I'll put it up top actually, because this guy gets piped down and I don't want to be routing it upwards. And yeah, my -128 is necessarily in the bottom, while this decoder doesn't really matter. So that's the first thing I'll do. I'll try to clean it up and I'll be back. I think I may have just discovered the bug in the game. I don't think I'm supposed to be allowed to move these. Because, can you hear that? Yeah, when I try to move it, it doesn't move. But then when I selected a bunch, I am able to move this around. So I'm not actually sure if I'm supposed to or not supposed to move to be able to move these inputs and outputs in this level. I mean, it is gonna be nicer with the inputs moved. Yeah, and the same goes for the output as well. I cannot move it, but I think if I select it along with something... No, that's also not working. How about something insane? No, it's still... Oh, is it because I was dragging? Yeah, I see. I get it. So you can do multi-select and then you can move things. And if I multi-select and I drag using the a draggable thing, then I can actually drag the output around. So that's actually a bug report. I need to send that to the developer. So I'm guessing I'm not supposed to be able to move this, right? If I select this and try to move that. Okay, so does this mean... Let's try to be fair. Let's make a new schematic with default inputs. Unmoved. Whatever. And let's try to work with this. I mean, they're basically torturing me at this point, but... Okay, I'll re-implement this in the fresh schematic. And then I'll be back. Okay. Something to this effect. I'm not happy with how this turned out, but can't really do much better. It's an awkward number of triple ORs if you're trying to do if you're trying to check for a non-zero number. Is there a better way? No, I don't think there's a better way. I think this is literally the best I can do. Okay, so yeah, we now have our purple line, which is non-zero, and we have our red line, which is below 0. And from them, we can decode everything else. How am I going to do that? Okay, so I think I need a bunch of ends. Do I need 8 ends? I feel like using 8 ends, but also 8 ends seem like re-implementing a component. 1, 2, 3, 4, 5, 8. This seems like I'm re-implementing a component. But I don't think... Yeah, I do need 8 different outputs, don't I? Wait, what do I even output? Yeah, I output a boolean. Okay. Output a signal. A single bit. So... What's up? Yeah, I don't have anything better, do I? XOR 1-bit decoder. No. I think I think there's nothing better than AND except for the switch. Again, shout out Christopher Iman 4921 for suggesting switches. Was it here? Or was it... Yeah, also little box can be completed using the switches, which I agree, makes sense. And it's even kind of more, you know, intuitively sensible, I feel like. We can use the switches instead of ends. And wait, actually, yeah, I wouldn't be able, because I was intending to pipe all the ends into the same output, and that wouldn't work. So I actually kind of have to use switches here. But yeah, this is gonna be a bit of a huge contraption. I'm not sure how this is gonna work, but let's save a lot of space and let's try to... So this is our output line. Oops. I need to connect them all up. This is our output line, and actually, I can already pipe the decoder. Yeah. So the switches, the inputs to the value, or the inputs to the switches are going to be the actual values I calculate from logic. But which switch is active, which thing I output, is going to be determined by our decoder. So let's use, I don't know, gray for switch selection. So something, oh no. Oh no, what am I? Oh my goodness. Oh my goodness. This is gonna be, there's gonna be 8 lines here. By the way, why have I never done this? 1, 2, 3, 4, 5, 6, 7, 8. No. No, absolutely not. Unacceptable. This is unacceptable. How do I improve this? Maybe put these lines on the other side? You know, push the switches slightly this way. And then... No, but I will also need to pipe this to the lines. Which, this is fine because I can rotate my decoder. Yeah, the only question is the actual lines. How do they go? That's no problem, but how do I, where do I put the lines? Can I... Should this perhaps be my setup? This doesn't seem too bad, does it? And then I'll have at least some space here. Yeah, let's do that. Let's put the decoder up here. Is this right? Yeah, this is gonna be correct. So 1, 2, 3. Connect all these up. And then do this crazy wiring job. 2, 3. Oh, actually, this kind of allows me to squish the switches up. Yeah, because you cannot... Oh, you can! Oh, okay, so I can even squish these. Let's squish them, I guess. Nah, maybe let's not. We'll see. We'll see what I actually need. But let's wire these for now. Like so. None of this matters. Oh, and that allows me to move my stuff closer to the output, which is appreciated. I want a lot of space to play around with. Or to play with. That's our output line. Okay, so this gets piped up there. Let's do this now. Oh no. I don't know. Whatever. Leave it for now. Okay. So let's start with the easy part. If our bit code is this, then we need nothing. Now let's also add a always on line, which I don't need an always, I don't need to waste an on switch here. I'm gonna be slightly more frugal, if you will. This is gonna be condition number 1, 2, 3, 4, 5. Condition number 5, 1, 2, 3, 4, 5. If I have my switch unlocked, then I also have the signal. So that will be it. Now, this needs nothing. You know, I can put a red wire here, but oops. This needs nothing. And wait, are these are 8-bit switches? I need 1-bit switches. Sorry. It's okay. It's fine. It's fine. They're the same shape. They're the same shape. We're good. We're good. Stop piping bytes, please. All right, now, if value... So what's the... Well, nothing is... No, the farthest thing from what we have is gonna be... I have no idea. Okay, let's just do them one by one. If value equals 0, so we need to negate not equals 0. We take negation, like so, and then we use our... You know what? I think I might want to take this down, straight like so. I think I will be reusing this a bunch. Well, I know I'm going to be reusing this a bunch. And I might as well do the same for this guy. You are in the way, please go away. Please, okay, go away. Alright, and this is gonna be my greater than 0 line, which is also gonna get used. I'm gonna remove the comments later. So, equals 0 is not equals 0. Now, less than 0, we already have directly, like so. Less than or equals 0 is actually, okay, you know what? I'm gonna optimize here. And I'm gonna add a equals 0 line. So this is still not equals 0, but equals 0 line is gonna be light blue. This is our equals 0 line, and I pipe it as the output to my equals 0 question. And also, less than or equals 0 is exactly less than or equals 0. Like so. So, equals 0, or I should use the dropper more, or that. Cool. Now, not equals 0 we have directly. Next, greater than or equals 0. I do not need a greater than line for this, because greater than or equals 0 is exactly the negation of less than 0. So I can take... Where is my negation? I can take a negation here. I negate my red line, less than 0. And this is going to be greater than or equals 0. And then... Okay, I want to move this all up, can I? I cannot. Whatever. And now the final value is greater than 0, which is the most complicated one. Well, it's not difficult, it's just gonna require the most operations, I believe. Yeah, I need not equals 0 and greater than or equals 0. So I need to or I need to end this with not 0. So let's add an end. Still feel like this could be improved somehow, but let's go over this for now. Right, we have this. Let's not use wrong colors. Right, and then we need to be not. We need another not. We need to be not this. And that's gonna be our final thing. Cool. Let's check if this works. I think that's it, right? It's broken. Why? No, this is not this is not a helpful debugging message. I have 123. My condition is never. Did I wire something wrong? My condition is never. never. 0, 0, 0, 0. No. Wait. No, 0, 0, 0 is never, and we should be... Okay, we're somehow decoded into the wrong... Oh. I see. I'm I'm decoding the absolute wrong thing. Okay, so this is the instruction. I'm decoding my number as the instruction. It's fine. That's fine. Cool, let's check now. Wrong. Okay, what's broken? If value greater than 0, output something. What's wrong with my greater than 0? We have... Wait... Oh, I'm using... Yeah, I've wiped the wrong thing here. Yes, exactly. I need not equals 0. Like so. Success! Cool. So that's my solution to the conditions problem. Your circuit has been saved to the component factory. Thank you. I wonder what would happen if I were to actually move these inputs and outputs using the bug. Okay, I'll clean this up real quick, just as I like to do, and I'll be back. I also unlocked the manual entry. Let's take a look at that first. Instruction. A byte, or a few bytes, sure. Opcode. The part of the instruction that determines which operation... Wait, what? I don't get what the difference between an instruction and an opcode code is. Oh, so an opcode is the part of the instruction. But what other parts of the instruction are there? Memory address. Oh, maybe memory address can be part of the instruction. Number used as a name for memory locations. These are used to specify where an instruction is supposed to load data. Jump, changing the value of the program counter. Changing which instruction is loading next. Is loaded next. Okay. 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 This makes sense. Yeah, I've heard these words, of course, but not in particularly deep terminology. Okay, as promised, I will clean this up slightly and I'll be back. I couldn't do much. I've actually tried for a while, but this is the best I could do. I tried turning it upside down, but the decision to have the 128-bit at the bottom, or rather, because the 128-bit is at the bottom, the decision to put this up was kind of important. So yeah, most of the circuit, I'd say, is fairly good, fairly neat, with the exception of this one. This part, the opcode. I believe this is gonna be called the opcode now, right? Yeah, this is messily piped into there. And also there's one more choice, one more decision I made. I decided to have my 4 lines for all the basic things, right? 0, not 0, greater than, less than or equal, or rather, actually, you know what? Let's add the comments for everything here. First of all, this comment is broken now. So let's say this is gonna be our less than 0, right? Our purple line is not equal 0, right? Our light blue line is equal 0. Where do I put the comment? I guess right here is okay. This is equal 0. Oh, come on. Can't see the comments at all. Oh well, and this is the negation of less than 0. So this is going to be greater than or equal to 0. And that's all we have here. Let's test. Is this successful? It says if value is zeros, output this looks like an error. But it suggests overwriting. Yes, I will overwrite, because I think this is better. I mean, I could actually condense it, you know, vertically. But whatever. I've spent enough time on this. This is gonna be me. And this video is already pretty long, so I think that's enough. And we will proceed with the primary Turing Complete line next time.